So last session we discussed the first Sylow's theorem. It gives an idea of the size of the subgroup, whether a subgroup exists with a specific order. In particular, if G is a group with order p to the power of n times m, where p is a prime and p does not divide m, then we showed that G has subgroups of order p to the power of 5 for all 1 less than or equal to I less than or equal to n. In other words, if Pn divides the order of G, that implies there exists a subgroup of order p to the power of n, or any pi where I less than or equal to n, 1 less than or equal to. So in here, the biggest p groups, see all these subgroups are p groups because its order is pi. So we have a theorem which says that G is a p group if and only if the order of G is equal to p to the power of n for some integer n. So every such subgroups are p groups, but the maximum size of the p subgroup in here is p to the power of n. We don't have any p subgroups of G that contains the subgroup of order p to the power of n. So that is a maximal subgroup. So if we take the order of G is equal to 40, which is equal to 2 cubed into 5, then the order of the largest two subgroup is 8. We have two subgroup of order 2, we have two subgroup of order 4, and we have order 8. And that is the maximum. So the maximal such p groups of G is called Sylow's p subgroups. Here the size of the Sylow's p subgroup is 8. So the definition goes like this. If G is a finite group and the prime P divides the order of G, then the maximal P subgroup of G is called Sylow's P subgroup. And that implies no P subgroups properly contains Sylow's P subgroup. It's a maximal element. But these Sylow's P subgroups are not unique, meaning there can be more than one subgroup of order 8 of a group of order 40. So the second Sylow's theorem gives a nice relationship between the Sylow's P subgroups. Okay, so let us start the Sylow's second. The Sylow's second theorem states that any two Sylow's P subgroups are conjugates. So second Sylow's theorem. If P1 and P2 are Sylow's P subgroups of a finite group G, then P1 and P2 are conjugate subgroups of G. Conjugate subgroup of G means P2 can be expressed as XP1 X inverse for some X in G. That means XP X inverse P belongs to P1, where X belongs to G, for some X belongs to G. Proof is not very complicated. Let us start the proof. The proof goes almost the same type of logic that we have been using. So here, let L be the collection of all left cossets of P1. So that means the number of elements in L is equal to G P1. P1 is a Sylow P subgroup, and that means the order of P1 is equal to P to the power of n, where n is the largest integer such that P to the power of n divides G. So that implies P does not divide GP1, and that implies P does not divide the size of the collection. Now define a map from P2 cross L to N such that Y times elements in L are of the form xp1, left coset of p1, is equal to yx p1. This of course is a left coset of p1, so it's the map is well defined. Verify if this map is a group action. It's a group action. And that implies L is congruent to LP2 because P2 contains P to the power of n elements for some n, integer n, mod P. And since P does not divide L, this implies LP2 is not equal to 0. If this divides P, then this is going to be 0. And what is LP2? Is actually elements from L such that yxp1 equal to xp1 for all y in P. And that implies xp1 belongs to LP2 implies yxp1 is equal to xp1 for all y in P2. And that implies x inverse yxp1 is equal to, this is p1 for all y belongs to P2. So this implies x inverse P2 x is equal to P, or you can say, to be sure, less than or equal to P, or a subgroup of this. But the order of P1 is equal to order of P2 because both of them are Sylow P subgroups. So their order are same. And that implies x inverse P2x is equal to P1. And that implies P1 and P2 are conjugates of groups of the third Sylow's theorem gives us an idea of how many Sylow's P subgroup exist in a finite group. So third Sylow's theorem. So let G be a finite group and P divides G. P is a prime. Then the number of Sylow's P subgroup of G is congruent to 1 mod P and divides the order of G. We'll take an example here to illustrate what this theorem means. Let us assume that the order of G is equal to 40. And we are trying to find out the number of Sylow's two subgroups. Sylow's two subgroups. That means the subgroups of order 8, because this is equal to 2 cube times 5. So here P is equal to 2, N is equal to 3, M is equal to 5. This theorem states that the number of two subgroups, Sylow's two subgroups, is congruent to 1 mod P. P is 2. So it could be just 3, because 3 is actually congruent 1 mod 2, or it could be 5 mod 2, it could be 7 mod 2. So are odd numbers, and this should divide G. That is, these number, when you take these odd numbers, that should divide 40 also. So this is not possible. Of course this is possible. So find out any other even number that divides, any odd number that divides 40, which is not there. So there are only 5 Sylow's two subgroups. So there are 5 subgroups of G of order 8. And that is what this theorem says. Now let us do the proof of this. Proof. See, here what we are going to do is let L be the collection of all Sylow's P subgroups of G. And we'll take one element from this collection. So let P belongs to. Now let's define a map from P times L to L by we'll take an element from here, x times t is equal to xt x inverse. That means you are taking t to its conjugate. So this conjugate actually belongs here because P is a Sylow P subgroup and T is a conjugate of this. So this is a previous theorem. If P is a Sylow P subgroup and T is conjugate to this, then T is also a Sylow P subgroup. So it's well defined, and verify that this is a group action. So this map is a group action. Verified. Now, so we can say that L is congruent to LP mod. Okay, what is in L? L contains all the Sylow's P subgroup. So if you can prove that LP contains only one element, we are done. So what is in LP? LP is equal to T belongs to L such that xt x inverse is equal to T for all x in P. That is the definition of LP. It is the one element orbit. But what does this mean? If x, this implies if x belongs to P, implies xt x inverse is equal to T, and that implies x belongs to MT, and that implies P is a subgroup of MT. And we also know that T is a subgroup of MT. MT means the normalizer of T. And T is normal in NT. And that implies if T is normal in NT, every conjugate of T is T itself. If it is normal, then the conjugate is itself, right? Because xt x inverse is equal to T. This is the conjugate. Okay, so when T is normal, this is true, and that means xt is equal to Tx. So there is only one normal if T is normal, all its conjugates are T. So all T's conjugates are same as T. So that means P and T are conjugates because they are Sylow's P subgroups. So P and T are conjugates implies P is equal to T. And that implies in here there is only one element. That implies LP is equal to 1. And that implies L is congruent to 1 mod. That is the first part, and which we still have to prove the number of Sylow P subgroup divides G. So the second part, we need a result from group actions. So if X is a G set, then Gx, this is the length of the orbit containing X, is equal to the index of G over the isotropic group of X. So we are going to use this result in here. So here again L is a collection of let L be the collection of all Sylow's P subgroups. But instead of taking the action from an element of here, we are going to take the action from G itself. So define map from G cross L to L by a G of T is equal to G T G inverse. What does this mean? This contains all Sylow's P subgroups. So all the, if you take any two elements, they are conjugate. Any two elements. So that means L contains only one orbit. This implies L contains only one orbit. Okay, so L is equal to the length of the orbit containing an element. It contains only one orbit, and so the length or the number of elements in here is the number of elements of the orbit containing P. And this is, using that, will be G over Gp. And Gp divides G. And that implies the order, the number of elements in L divides G. And that is a second step. This is the number of, see, L is the collection of all Sylow's P subgroups. and it does, and its number of elements is equal to number of elements in the orbit containing p. There is only one orbit, because any two elements, if you take, they are conjugate. So one element can be reached by the other element through the conjugation. So there is only one element, so one orbit. So the length of the collection is equal to the length of the orbit, and that is equal to this, and this divides G. So the number of Sylow's p subgroups divides the order of G. Let us do some examples on the Sylow's p subgroups. The first example that we want to try is, we've already done one, but we'll do one more. Find the order of Sylow's 3 subgroup of a finite group of order 54. So 54 is equal to 2 times 3 cube. So the order of Sylow's 3 subgroup of G, this is order G, order of G is 3 cubed, that is 27. There is no bigger 3 subgroups of G when the order of G is 54. This is the maximal 3 subgroups. We'll do another example. Find the number of possible Sylow's 3 subgroups of a finite group G of order 255. Here we are going to find out the order of the Sylow's 3 subgroup. Here we are going to find out the number of possible Sylow's 3 subgroups. So here we are going to use the third Sylow theorem. So the number of Sylow's 3 subgroup of G is congruent to 1 mod 3. That is, possible number of Sylow's 3 subgroups of G are 1, then 4, 7 dash dash dash. Okay, but number of Sylow's p or 3 subgroups should divide 255. So the possible number of Sylow's 3 subgroup are 1 divides 255, so 1 can be a candidate. 4 is not a factor of 255. So if you go like this, the next element in this sequence will be 85. 85 divides 255, and 85 is mod, 85 is equal to mod 1 sorry, is congruent to 1 mod 3. Right? So these are the possible number of Sylow's 3 subgroup of a finite group G of order 255.